Welcome. In this video, we are in Chapter 4, and we will look at Part C, GCF and LCM. That's greatest common factor and least common multiple. We'll take a look at what those things really mean, calculating those things with the slide method, and then calculating greatest common factor and least common multiple with prime factorization. Let's go. So, multiples of 6. We can see how they begin. 6, 12, 18, 24, 30. But let's take multiples of a different number. How about 9? Here are some multiples of 9. 9, 18, 27, 36, and so on. And we see that there are some common multiples. 18 is in both lists, and also 36 is in both lists. 54 is in both lists. So they share some common multiples. But often we're interested in what is the least of the common multiples, and the least common multiple is 18. So we might write LCM of 6 and 9 equals 18. That's how you might see it. Or just simply, the LCM of 6 and 9 is 18. Well, instead of multiples, let's think about factors. Here are the factors of 100. Now this is a finite list. Do you remember previously when I was looking at multiples, the multiples went on forever and ever. But for factors of 100, I only have a finite number of those things. Well, we'll take the factors of something else. How about the factors of 75? Here's another list. Once again, these two lists share some common elements. 1 is common to both, and 5 is common to both, and 25 is common to both. So 1, 5, and 25, those are the common factors of 75 and 100. But we might be interested in the greatest common factor. And the greatest common factor in this case is 25. The least common factor isn't very interesting. The least common factor will always be 1. So when I'm looking at factors, it's always the greatest one that's the interesting one. We write this as the GCF of 175 is 25, or you might see it in this functional notation, GCF 175 equals 25. Okay, here are some word problems. Crackers come 24 per pack. Cheese slices come 20 per pack. And you really want to have the same number of crackers and cheese slices. Of course, why wouldn't you? So first of all, if I buy enough crackers and cheese slices so they match, how many will I buy? All right, let's start figuring it out. So crackers come 24, or if I buy 2 packs, 48, or if I buy 3 packs, 72, or if I buy 4 packs, 96. Okay, maybe that'll be enough. Let's see here. On the other hand, cheese slices. Let's see, if I buy packs of those, see here, 20, 40, 60, 80, 100, 120. I don't see a match yet. Maybe I need to continue my crackers a little bit. What's after 96? Let's see, 96 plus 24. Oh, there's 120. So there it is. So it looks like if I buy enough packs of crackers, I can make 120. And if I buy enough packs of cheese slices, I can also get it 120. So there it is. I am satisfied. I know that I can have 120 crackers and cheese slices. They will match up beautifully. But now that I know 120 is the total number, let's back up a little bit. How many actually packs of crackers should I purchase? So at this point, we need to take our 120 and think, how many times does 24 go into 120? How many of those do I need? Now, from the list above, we can see it's 1, 2, 3, 4, 5 packages. Or we could figure this out as 120 divided by 24 equals 5. And how about the second problem here? How many packs of cheese slices should I buy? So again, it's 120 total slices, and I start off with 20 in a package, and I could read off from the list 1 package, 2 packages, 3, 4, 5, 6, or we'd think 120 divided by 20 equals 6. So I'll need 6 packs of cheese slices. Here's a different kind of problem. I have 36 stickers and 48 dimes. I want to make gift bags that each contain the same number of stickers and dimes. So what I mean is that every bag has the same number of stickers and every bag has the same number of dimes. How many gift bags can I make? Well, I have a lot of options. I could make one gift bag, right? And the people that come to my party, there's only one person who gets a gift bag, and that one person is very lucky. And that one person gets 36 stickers and 48 dimes. That wouldn't be good. Probably a better situation. Well, I don't know. Could I have two gift bags? If I had two gift bags, let's see, my stickers would divide in two, so I'd get 18 stickers and 18 stickers there. And the 48 would also divide by two. 40, whoops, so 24 dimes in one bag and 24 dimes in the other bag. Okay, well, I'm going to keep experimenting on this, right? I mean, I would do one more solid example. How about three? Could I make three gift bags? All right, let's try this out. All right, if I had three gift bags, my 36 stickers would divide by 3. I get 12 stickers in each bag. 12 stickers, 12 stickers, 12 stickers. And my 48 would divide by 3. 48 divided by 3 is 16. I have 16 dimes, 16 dimes, 16 dimes. All right, so I can split things up nicely if I have one bag, or if I have two bags, or if I have three bags. Maybe the real question is, what's the most number of gift bags that I could make? And what's nice about 1 is that 1 divides evenly into 36 and 48. And what's nice about 2 is that 2 divides evenly into 36 and 48. 2 is a common factor of 36 and 48. And 3 is a common factor of 36 and 48. Now, as a counterexample, 5. I couldn't make 5 gift bags because 5 does not divide evenly into 36 and 5 does not divide evenly into 48. So I need the greatest common divisor, the greatest common factor of 36 and 48. So my factors of 36 are, all right, and my factors of 48, those look like, and then I look for my greatest common factor. Let's see, what is it? 16, 18, 24, oh, 12. I think 12 is the biggest number that goes into both of those. So I could make 12 gift bags. That's the most number of gift bags that I can make, where each gift bag has the same number of stickers and each gift bag has the same number of dimes. So how do we actually compute least common multiple and greatest common factor without always having to list out all the factors or multiples? I'll present two methods. The first one is called the slide method. So let's find the least common multiple and greatest common factor of, say, 900 and 360. So the first thing I do is I just put those two numbers side by side and I make this little angle bracket underneath it to the left. And I ask myself, can I think of any number that's common to both of those, any factor that they have in common? It doesn't have to be big, it doesn't have to be small, just anything. For example, I might see that 2 is a common factor because both of those are even. Or maybe I'll see that 10 is a common factor because they both end in 0. So in fact, let's take 10 as that common factor. Once I identify something, I divide 10 out of both of those numbers. And there we go, and we put the results down below, 90 and 36. Now, I look for a common factor again. Can I see anything that's common to both 90 and 36? Oh, how about 3? And again, this is where divisibility rules really come in handy. You can do these things at least you can identify factors by hand very easily, and then use your calculator to divide out. All right, so when I take 90 and 36 and I divide each by 3, I get 30 and 12. Let's keep going. And basically, we're going to keep doing this until I can't do it anymore, until I have to stop. 3 is a factor of those. I'll factor out 3. 10 and 4, do you see a common factor? At this point, I think the only common factor remaining is 2. I divide out 2. I get 5 and 2. And at this point, I'm done. 5 and 2 have no common factors. Actually, there's a word we use called relatively prime when two numbers have no common factors other than 1. So 5 and 2 are relatively prime. 5 and 2, that's the end. Now that I have this list of numbers, here's what I do to compute least common multiple and greatest common factor. The greatest common factor is the product of the numbers on the left. All right, greatest common factor, that's the product of the numbers on the left. But the least common multiple, in order to get the least common multiple, I'm going to do the numbers on the left and the numbers on the bottom. I multiply those together. And look at this. Isn't this nice? This shape, it makes an L. So this is how you can remember L for least common multiple. I multiply all the numbers together in the shape of the L. And then also just for greatest common factor, it's only the items on the left. But it's kind of cool. It's almost like magic. You multiply them together and you get your answers. Curiously, there's another way to compute greatest common factor and least common multiple. The greatest common factor also turns out to be 900 divided by 5. It's like you take the top number and you divide by the number you got at the very bottom. 900 divided by 5 ends up giving you 180, and that's your greatest common factor. Or I could take 900 and multiply by 2, so I'm going across and I'm multiplying, and I'll get 1800. That's our least common multiple. So that's really kind of curious. I can just look at the numbers at the top and the numbers on the bottom and do that trick to find my GCF and LCM. Also, we can see this, it's 360 divided by 2. So 360 divided by 2 is my greatest common factor. Or I could take 360 times 5, 360 times 5, and that'll give me the least common multiple. One last observation. If I take the fraction 360 over 900, so I imagine there's two numbers on top. If I was to make a fraction with them, it turns out that the reduced fraction is the fraction that I get with the numbers on the bottom. So 360 over 900 is the same as 2/5. That's kind of cool. Here's another method, and it's really the more traditional way of computing the greatest common factor and least common multiple. All right, let's say that the numbers I want to work with are 60 and 1050. How do I find the greatest common factor and least common multiple? The first thing I do is find the prime factorization of those two numbers. So here it is, I've written it out already, but maybe you could use a tree method or some other way, a calculator, to find the prime factorization. And I don't write this with exponents, so I'm not actually writing 2 squared times 3 times 5. I'm really just writing the entire thing out with repeated factors as needed. All right, so then once I have that, I imagine two circles where one circle represents the factors in 60 and the other circle represents the factors in 1050. And I begin by looking at what are the common factors in both. In fact, maybe I'll make a little bit more room there. There we go, more room in the intersection. So I see that there's a common 2 that's in both. So I'll write 2 in the intersection and I'll cross off the 2's. Those are handled. The next thing I notice, there's 3's that are common. So I'll put 3 in the middle and I'll cross off both of those 3's. And it looks like there's a pair of 5's that's common. I'll put 5 in the middle and I'll cross off both of those 5's. Now what remains in the 60 that I haven't crossed off? It's a 2. And what remains in the 1050 that hasn't been crossed off? That's 5 and 7, 5 times 7. And now look at what we've done. In the picture on the right with the 2 circles, the primes inside of 60, those all multiply to make 60. And the primes inside of the 1050 circle, multiplying those together makes 1050. It turns out that my greatest common factor, that's the stuff that's common to both, the greatest common factor. So that's my 2, 3, and 5. So 2 times 3 times 5 is 30. 30 is the greatest common factor. Or if I want to find the least common multiple, I multiply all the primes in this picture. 2 times 2 times 3 times 5, so that's the first 2 times 3 times 5, plus the times the 5 times 7. So if I multiply all those numbers together, I get 2,100. And so that's another way, using prime factorization, that I can compute the greatest common factor and least common multiple. All right, so that completes this section on greatest common factor, least common multiple, what they are, how to think about them, and 2 different ways for computing them.